So this parallel session will be recorded. Okay.
I think I'm recording already. I had a message. Okay.
So let us start our parallel session. So entitled Heteroclinic Dynamics and Beyond. On behalf of SPM, the national meeting, I would like to thank the speakers, Sophia, Alexander, Chris, and Peter. I organized this parallel session with Telmo Peixe. He's not here because he's having some problems with the access. The first speaker will be Sophia Castro. Sophia Castro is from Economics Faculty of Porto University, and she will talk about the asymptotic stability of AC networks. Let me inform you that you have 15 minutes plus 5 for questions, okay, and discussion. Okay, go ahead. Thank you, okay. Sophia.
Thank you very much. Let me start by thanking Alexander and Telmo for organizing this session, and in particular for having invited me. It was a pleasure. And this is a joint work with Isabella Burior, whom I've sort of realized was attending, and Olga Podvigina. And if I manage to make you curious enough, you can read about it in Nonlinearity. It came out last year. So I would like to start with some notation, which is, I guess, from the audience, almost unnecessary, but let's just go through it. I'm looking at a very simple, well-behaved differential equation. I'm going to use Xi for denoting equilibria. And then these equilibria, when they're connected in a cyclic way, and they're different, we call them a heteroclinic cycle. And when we put a finite number of these cycles together in a connected way, we call it a heteroclinic network. I would just like to spend a little bit more time on distinguishing these two notions here. And you can have, of course, you have a connection, so there has to be a trajectory going from the beginning equilibrium to the end equilibrium. And if you look at Xi I to Xi j, you have this connection, this trajectory here. And if you look at the unstable manifold of Xi I, stable manifold of Xi j, intersect them, and you have exactly the same thing. So this is a case where the full state of connections is a connecting trajectory. But then if you look at Xi I to Xi k, you also have something that looks very similar. This is a connecting trajectory, but then the full set of connections is the whole of this, the interior of this triangle. So you actually have an infinite number of trajectories connecting the two equilibria. And this is a picture that is going to be very usual and will appear many times in this talk. And you can see it in the graph of a network. So a network can be represented by a graph where the equilibria correspond to the nodes and the connections to the edges. And I'm going to be showing graphs whenever I'm talking about networks in this talk. So you have a triangle in the graph, which is not a cycle. So you go from Xi I to Xi j, then to Xi k. For having a cycle, you'd go from Xi k to Xi I, but you don't. You go the other way around. And we call this a delta clique. And this is something that was defined together with Alex and Pete by looking at the graph. But then when you're looking at dynamics, this kind of triangle in the graph, so a delta clique in the graph, will support two very different kinds of dynamics, which are these two down here. And for studying stability of networks, it's important to distinguish between the two. So in this talk, a delta clique is going to be something that has, well, this shape in the graph, but then the unstable manifold of Xi I is all going to be converging to Xi k. And here you can see that there's a little bit of the unstable manifold of Xi I that is not going to converge to an invariant set that is pat of this structure that I'm interested in. And that's the main point when thinking about delta cliques, which is, of course, controlling the unstable manifold in equilibrium. And this is something that is very important when you're studying stability. You have to, if you want something to be stable, the unstable manifold cannot do very strange things. So this is exactly what Mike Field did in 2015. He defined a clean invariant set by saying the unstable manifolds of invariant subsets is contained in the big set. So the way to think about this for this talk is X is an equilibrium in the network. You want for the network to be clean, you want the unstable manifold of all the equilibria to be part of the network. And so we come up with a definition, which is an AC network, and AC stand for axial and clean. So clean has to do with this last bullet, the network is clean. The axial has to do with the placing of the equilibria. So they're going to be on the coordinate axis and only one equilibrium per axis. We want the ODE to be Z2N equivariant, so there's a reflection on each of the axes, but we don't want to deal with all the images in the group orbit of the equilibria and the connection, so we're going to restrict it to the positive part of the state space. So this is, in a way, a definition with a lot of structure, but then it creates enough interesting networks that allow us to say something about stability, and that's what I'm going to say. But before going to stability, I would like to show you, give you an idea of how to think about an AC network, or what is not an AC network. And what's not an AC network is, for example, this very famous example of the Kirk and Silver network, where you have two cycles with 3 nodes each, like this. And what happens here is that the unstable manifold of Xi2 is 2-dimensional. And then some of it goes to Xi3, some of it goes to Xi4, and then of course some of it goes somewhere which is not this network. So in order to make this clean network, you need to put in a delta clique here by adding a connection. You could have added it the other way around, it doesn't really matter, not for now, so that you can capture or sort of control the unstable network of Xi2. So there are not very many networks in AC networks in R4. There's of course many networks in R4, not AC networks in R4. There's only 2 actually. So you have this one that I just showed you that you get from introducing a delta clique in the Kirk and Silver network. And you have this one, which starts out with a 3 cycle here. And then the other equilibrium, so you're in R4, so you need the four equilibria. This equilibrium here is going to make Xi1 have a 2-dimensional unstable manifold, and for the network to be clean, you need to add this connection for controlling and making the unstable manifold of all the equilibria part of the network. We're of course assuming that the directions that are not being used for connections have contracting eigenvalues, so there's no stable manifold there. When you move to R5, you still only have 2 networks, AC networks. Whenever I say network, I mean AC network in this talk. The one on the right appears in the famous game of rock, scissors, paper, lizard, Spock. It also has very many of these 3 cycles, which are going to correspond to the rock, scissors, paper game. And this one here on the left, if you look at it carefully, is actually obtained from the network that was on the left in R4 by adding this Xi5. And of course, what happens is that there is a 2-dimensional unstable manifold here at Xi2, which then you have to make sure that it's part of the network. So you then add this connection, creating a delta clique. This connection from Xi5 to Xi1 is actually optional. So you can either put it here or not, because it's not necessary to contain the unstable manifolds. And this idea that I'm trying to tell you about, this construction idea, is actually the construction idea for AC networks. It's a very systematic process. And there's a theorem that tells you how you start building these AC networks by making sure that you can control all the unstable manifolds by adding delta cliques whenever an equilibrium is causing a problem, or adding dimension to the unstable manifold. But I'd rather not talk about that. I'd rather talk about asymptotic stability of these networks. And the theorem has one disadvantage, in my opinion, which is that it's only a sufficient condition. On the other hand, it's something that's very easy to calculate. It's very systematic to use. And therefore, when it works, it's very easy to implement. And so let me go through it in a little bit more detail. So you have a network, which is Y, and then you look at all the cycles that you can see in this network. And for each cycle, you construct a quantity. And if this quantity is greater than 1 for every cycle, then the network is asymptotically stable. And the quantity is a product. And these rho j's are calculated at, so there's one rho j per node. So if you have m equilibria in a cycle, then you'll have m rho j's. And this is just the usual quantity that compares the strength of contracting eigenvalues to the strength of expanding eigenvalues, or transverse eigenvalues with expanding eigenvalues. So saying that this rho is bigger than 1 is the product of the relative strengths of contracting and expanding is bigger than 1. So contracting is stronger than expanding, and that gives you asymptotic stability. Now, what I would like to do is tell you a little bit about how to calculate this rho j. And the calculation of the rho j is directly related to whether you're calculating it at a middle point of this delta clique or not. So you have a B point, a beginning point, where everything goes out. You have an end point, everything comes in. And then you have the midpoint, which is the one that is in the middle. And you talk about the short connection, which is the one that goes in a way directly. And then you talk about the first long and the second long connection. Of course, these are not connections from psi I to psi k, but they're sort of accompanied by some of the connecting trajectories that go this way. So the calculation of the rho j depends on whether you have an endpoint or not. Let me start by looking at the case when psi j is not an endpoint. So using this network as an example, the only point that this doesn't apply to is psi 2, because psi 2 is an endpoint of this delta clique. Psi 1 is a B point, psi 3 is an E point, and psi 4 is simply not an endpoint because it doesn't belong to any delta clique, but the result applies. And because we want to have a quantity, so a product of these rho j's, which is bigger than 1, let me have a closer look at what these quantities might be. And in this case, the second quantity here, if the transverse eigenvalue is negative, it'll be bigger than 1. So that's good for asymptotic stability. And this quantity here is bigger than 1 if the contracting is stronger than the expanding. We're assuming that C is negative here, so this quantity is positive. So the rho j for something that is not an endpoint can be bigger than 1. It could also be smaller than 1, but it can be bigger than 1. And when we move on to endpoints, there's 4 ways in which endpoints can appear in AC networks. So the simplest one is what's depicted here. So you have an endpoint for just one delta clique, and there's only one expanding eigenvalue, which is this one. Then the rho j is equal to 1. So if you're really looking for asymptotic stability, if all the rho j's are equal to 1, you're not going to have a sufficient condition. You don't satisfy the sufficient condition. Then you can have an endpoint for only one delta clique, but with a second expanding eigenvalue. That's the case of this psi j, this psi 2 here. So it's an endpoint for just this delta clique between psi 1, psi 2, and psi 3. But it has 2 expanding eigenvalues, the one going towards psi 3 and the one going towards psi 5, sorry. Then the rho j is this quantity, and this is clearly less than 1. The C is a negative, so this is less than 1. You can have an endpoint for more than one delta clique. What's drawn here is 2 delta cliques. Then again, rho j is the minimum of these 2 quantities, but then at most it's going to be equal to 1. And you start seeing the problem. If you have too many endpoints, too many delta cliques, then it's going to be hard to satisfy the condition for asymptotic stability. And the most complicated case is this one. So what's drawn here is psi j is the endpoint for 5 delta cliques, 3 on this side and 2 on this side. It has 2 expanding eigenvalues. the rho j is a bit nastier to calculate, but still these quantities, A1 may be bigger than 1, but A2 and A3 are always smaller than 1. So you never have xij that's bigger than 1. And the reason why this, then the theorem that I showed you is not necessary is if you look at this network, so the one from the rock, scissors, paper, lizard, Spock. I hope you can see the colors. I've colored the delta cliques and the endpoints of the delta clique in the same color. So Xi3 is underlined in pink, and because Xi3 is the endpoint of the delta clique that goes Xi5, Xi3, Xi1, and then Xi5 to Xi1. And you can see that all the equilibria are underlined in some color, and they all belong to this cycle. So this network has one cycle, at least this one. This is the cycle that looks like a star here inside the structure, such that all the equilibria are endpoints. So you're never going to have the sufficient condition in the theorem. However, it is possible to prove that there are parameter values in the construction of the vector field that make this cycle asymptotically stable. So there is still some better condition to be found. So this will perhaps be continued. It is being continued with Isabella Burion, Eliana Garrido Silva, and Ana Ferreira. So maybe next time we have a meeting, I'll have a bit more to tell you about. But for now, I'll thank you for your attention and leave you to the next speaker or any questions that you might have.
Okay. Thank you, Sophia. Thank you for your talk. So questions, some remarks? In the chat, I don't have questions. I have in fact two questions. The first question is the following. So we did the computations for R4 and R5, and this is valid for Rn, is correct?
Yes. It's valid for any. There's no constraint on the dimension.
Okay. So, but you need some general context of the network, or not? You need some hypothesis of the network to make this procedure for Rn.
It just has to be an AC network. So if it has all that structure in the definition, then you can apply this. Okay.
And finally, on slide 17, in this slide that you you said that under some conditions you could have a given cycle asymptotically stable.
The whole network is asymptotically stable.
Okay, even when the condition is not satisfied.
Yeah,
even when
this is an example that shows you that the theorem that we have is a sufficient condition, and it's not because we can't prove that it's not necessary, it's because it's actually not necessary. So this is an example that shows that the condition that we have is sufficient, but it's a bit too strong.
Okay. And in terms of the dynamics inside the network, so you know that the network is asymptotically stable, but dynamics inside the network, do you know something about this? Do you have some additional information about?
Claire Postlethwaite and Alistair Routledge know quite a bit about this, and a lot of people who work in population dynamics also know quite a lot about this. We're now trying to finish something that will tell you a bit about the stability of some of the cycles, and so hopefully putting all these things together, there will be some knowledge about what the network, what the dynamics is. But the thing is that even though this is, I mean, it's not a very complicated network in a way, but still the dynamics can be very complicated. So because the cycles don't have that much stability.
Okay, Sophia, once again, thank you for your talk and for this discussion.
Pleasure. Let me stop sharing.
Okay. Yes. So, Alex.
Yes.
Could you please share your file?
I am about to do so.
I know that Telmo is already here. I don't know if Telmo would like to present you, because Telmo, could you speak?
First of all, sorry for the delay, but I have here some technical problems. So hi everyone. Sorry, Sophia, for didn't assist to your talk, but you can see it later for sure. Well, let me introduce now Alexander Luz from the University of Hamburg. He will talk about creating almost complete and equable heteroclinic networks. So welcome to this talk.
Yes, thank you very much. Thank you for inviting me, both Alex and Telmo, and thanks for putting together this interesting session. This is about joint work with Peter and Sophia, who are both also here, as you have seen. And Sophia, I'm really grateful for your talk. Not only was it very interesting, you also did a lot of work for me and introduced a couple of things that I don't have to introduce now. So yes, thank you for that. Yeah, so this is about the question whether or how we can turn a directed graph into a heteroclinic network, in the sense that if we just start with an arbitrary given directed graph, can we write down a vector field that then has dynamics that correspond to this structure that we started out with? So if you just randomly clicked into one of the parallel sessions and you didn't know that the title of this session was Heteroclinic something, then if I draw something like this and ask you what it is, you will probably just say, well, it's a directed graph. There's some vertices and some edges, and they all have an arrow, and that's a directed graph. And as Sophia said, that is perfectly true. And it's a nice way of representing a heteroclinic structure. Okay, so these xi are just usually equilibria, but they could be something more complicated. And then an edge in this graph, we usually draw that to represent an intersection of unstable and stable manifolds of these two nodes in a system. But realizing that this is actually just a graph, we can turn the question around and ask, okay, if we don't start with a dynamical system and analyze its attractors and come up with a heteroclinic network, but if we just start by drawing a graph, can we then write down a dynamical system that, if I look at it, has a heteroclinic network that makes me draw exactly this graph? Okay, so I can put that a bit more eloquently like this maybe. If we start out with a graph, can we find a vector field, just some smooth f of x, so that we can consider this x dot equals f of x on Rn that has an heteroclinic network that corresponds to the graph in the sense that vertices and edges in G correspond to equilibria and connections so in the graph correspond to equilibria and connections in the heteroclinic network. And to take it a step further, I might as well then ask if I can do that under some circumstances, can I make this network that I generate have some nice properties that for some reason I might consider desirable? So could I make it asymptotically stable, or at least have some weaker form of attraction? That might be something I would like to do if I think of this in terms of modeling a certain phenomenon, where I maybe want to come up with a system that not only somehow possesses this structure in phase space, but I also want to know what exactly is its influence on the dynamics of this system. Okay, and here's some partial answers that are by no means complete due to the short time, but I still would like to let you know that the first part of this question has definitely been addressed by different authors previously. So, for example, Peter Ashwin and Claire Postles-Waite have a couple of papers on exactly this question of realizing a directed graph as a heteroclinic network. And there's two methods in these papers to do that. They both have some restrictions. One of them is the simplex method. So there they design a system where basically you get an axis for every node in your graph, and there's an equilibrium on each of these axes, and you have some z2 to the n symmetry where n is the number of equilibria. So this sounds very much like the AC networks that we just heard about. That's one way of realizing a graph as a network under some assumptions that I happily ignore for now. Another one in the same work is called the cylinder method, that has a geometrically different approach of putting all the equilibria you want on the same axis and then introducing into your system a new plane for every connection you want. And then yeah, if you want a connection from this first node to the second one, you need a plane that contains a connection like this. And again, under some little bit milder restrictions, you can turn a lot of directed graphs into heteroclinic networks. Mike Field has also been working on this. There's at least 2 papers by him on related questions in the context of coupled cell networks. If I were to draw a picture for this, it would look exactly like the cylinder method picture, but the meaning is a little bit different. So here the space, the one-dimensional space containing all these equilibria would be the full synchrony space, and then connections are achieved by desynchronizing and resynchronizing at a different value. So people have worked on this before, and we wanted to put a bit more emphasis on not just the question, can we do this, but what sort of properties can we guarantee that the network that we generate possesses? Because that's not necessarily an easy thing to answer. If you look at these methods here, it's quite a lot of work to just get the system with the network structure that you want, and then maybe you end up with something fairly complicated, and it's not so easy to tell whether what you've generated is asymptotically stable or not, or has some other properties. So I'll walk you through the rough ideas of our work by this example that you've also seen and probably know anyway, the Kirk-and-Silber network. This has been extensively studied over the last 25 years and more. So this is a network consisting of 2 cycles with 3 equilibria each, and they share this connection between Xi1 and Xi2. So this is the graph for this network, or the way we represent this network. You can think of it, if you like, as being generated by the simplex method, because it has equilibria on coordinate axis and connections in planes and so on. Of course, the simplex method came much later than this, but in spirit, it's the structure. It describes the structure of this network. And as Sophia already pointed out, when you look at this network for a little bit, you soon notice there's a 2-dimensional unstable manifold at this Xi2, and that means that if you look at the network that is made up only of these 1-dimensional connections, this will certainly not be asymptotically stable, okay? Because if you look at a cross-section that is sketched here, there's a 2D bit of unstable manifold that does whatever it does, but it certainly doesn't stay close to the 1-dimensional network here. And suppose I started out with this graph and wanted to realize it as a heteroclinic network that is potentially asymptotically stable, then I can't have something like this. Okay, I need to do something about this. I need to control this unstable manifold in the construction that I give you, because if this just goes off to infinity, then yeah, I don't know what it does, and this object will certainly not be contained in a fairly small, bounded, maybe attracting invariant set for the dynamical system that we generate. So if just thinking geometrically, you could draw 2 pictures that do the job, and one you've seen before, that is this delta clique kind of thing. So if I want a network like this to be embedded in an attractor that is not terribly much bigger than what I initially wanted here, then one way to do that might be to just force the dynamics to have an extra connection in one direction here, and just have all the rest of the unstable manifold of Xi2 go to this other equilibrium as well. Another way to do it might be to say, okay, if I introduce an extra equilibrium in this plane somehow and make it do the same job by bounding the unstable manifold of Xi2 by connecting to both equilibria, and then, okay, you need a connection from Xi2 to this new node eta, but then you can also just draw a picture that would nicely do what we want, okay? And now let's look at some similarities or differences between these 2 ways of thinking of generating something that gives you an attractor, maybe. One is completeness. That's related to the notion of clean that Sophia just talked about. So a network is complete if it contains all unstable manifolds of its nodes. This does not have the compactness condition that clean has had in Sophia's talk. This has the advantage that I can talk about it at the level of the nodes. So a node is complete if all of it complete with respect to a network, if all of its unstable manifold is contained in the network. So you see that whether or not an object is complete with respect to if the node Xi2 is complete in either of these drawings depends a lot on what you consider as the network. Okay, if you here take this whole thing as the network, so you add this extra connection which wasn't in the graph, but okay, let's do it, and include all the unstable manifold of Xi2. Well, okay, then you've generated a complete node because it just put all of the unstable manifold in it. Here it's a little bit more tricky. Okay, if you don't want this eta as part of your network, then even with this construction here, even if the dynamics was like this, you wouldn't have a complete node because there's still a bit of the unstable manifold going to eta, which is not part of the network. Okay, to sort of distinguish cases like this, which maybe I don't consider to be so bad, but still then they're technically not complete, we introduced the notion of almost completeness, which means being complete up to a set of measure 0 within the respective unstable manifold. Okay, so for example, this drawing here on the right-hand side, where I do not want eta as part of my network, would lead to an almost complete node Xi2, because all of the unstable manifold, if I consider these two-dimensional connections as connections in my network, all of the unstable manifold of Xi2 goes to Xi3 or Xi4, except for this little bit, this lower dimensional single trajectory that goes to eta. Okay. And another property that we're looking at is what we, after some discussion, called equability. So that is related to the question, if I have a node that has more than one outgoing connection, so like this Xi2 connects to at least 2 different equilibria, do all these outgoing connections have the same dimension? Okay, you see that it's not the case in this picture here. There's a 2D bit going from Xi2 to Xi4, but just the single connection, the single trajectory from Xi2 to Xi3. Here it depends again on whether or not you include eta in your network. Okay, there's a 2D connection to Xi4 and a 2D connection to Xi3. So if you don't count eta, I would call this node equable. But if I include eta in the network, then I have a one-dimensional connection to eta, so it's not equable anymore. And you see that this already looks like there might be a trade-off between completeness and equability in some instances. Okay, if I really want completeness, then maybe I have to live with the fact that my network is not equable. But if I put an emphasis on equability, then I probably have to live with almost completeness instead of completeness. And I like to think of this equability condition as a fairness condition. Remember, if we start out with a graph and you draw a graph and there's a node and it has 5 connections to different nodes, then and I'm supposed to realize it as a heteroclinic network, then I don't have an a priori reason to favor one of these connections over the others by giving it a higher dimensional connection. So maybe for modeling reasons, you might consider this desirable, okay, to have all of the connections prescribed by your graph be of equal dimension. Okay, so then this is a potential candidate for an asymptotically stable bigger network that contains this Kirk-and-Silber thing as a subnetwork. Just introduce your eta and then the connections we had on the earlier slide. The problem is that this eta might have transverse unstable directions. Okay, so eta, if you remember, is placed somewhere in this plane, and in all that I said until now, I was only worried about this plane and drew some pictures. Okay, and if I can write down a system that does exactly this, then I haven't thought at all so far about what happens outside of this cross section here outside of the space that this is contained in. Okay, and that turns out to be a real problem. That when you just do something like this and hope to sort of close off the unstable manifold by adding some node and then some connections and so on, then you have something transversely unstable possibly. Okay, last slide. So what's the result that we actually have in this paper that you can look up in the Journal of Nonlinear Science if you want? I hope that I've convinced you now that it's not a reasonable wish to say, I would like to be able to just draw any digraph and then write down a vector field that has this graph as an asymptotically stable heteroclinic network. That's probably not going to work because of this trade-off between completeness, which is necessary for asymptotic stability. Or well, at least if I add equability to what I just said. But I hope that I've managed to make you agree in this brief period of time that what's written here is sort of a reasonable wish. Okay, maybe I can realize a digraph as something that's almost complete within something that's not terribly much bigger, so some other network sigma prime, and do it in an equable way. The actual theorem that we have has some restrictions, so we have some restrictions on the graph that I'll not comment on. I'm glad you already know what a delta clique is. And the main drawback, I would say, is that we cannot prove asymptotic stability, but just closeness for now. We can handle a lot of these situations in specific examples in low dimension. It's not a problem to make this this Kirk and Silber thing to close it off and get something as asymptotically stable. But in general, so there's no restriction on dimension here. And in general, we're not able to prove asymptotic stability due to this problem that I tried to hint at with the transfer stability of these extra nodes that you somehow have to accept if you want completeness of your nodes. So that is it from me. Thank you very much. And I'm happy to take any questions.
Thank you very much, Alexander, for your excellent presentation. If you want any participant to write some question, comment, I can read it. So, well, I can go ahead, Elsa.
Go ahead. I have a question to Alex.
Yeah,
Alex, in this theorem, when
go. Sorry.
In this theorem, when you have sigma prime closed, what do you mean? Is closed in what sense?
Closed
topological
as a set.
sense?
Yeah.
Okay.
It's basically the way we create it is it's the closure of something, and it's the closure where we can write down a vector field that does more or less what we want. If we then take as the sigma prime the closure of the unstable manifolds of all its nodes, basically, and that will then automatically include some of these eta-like equilibria that we call separating nodes here. I didn't really explain that, so really just in that sense.
Okay, and the second question is that given a graph, you can construct a vector field in Rn. Could you find a minimal n in such a way that sigma prime is asymptotically stable? Because I think that, suppose that n is equal to 10. If you find a heteroclinic network that is asymptotically stable for R10, perhaps you can have this in R11, R12. Could you find a minimal n for which the cycle is asymptotically stable in Rn?
So that's a very good question. The n, so the dimension of the system that we generate, is the equal to the number of vertices in the graph. That's what automatically happens, because it's basically an extension of the simplex method that we use to generate this vector field. But the question of minimality is a good one. I don't think there's a lot of results on how to realize a graph in a system of minimal dimension. So I don't really have an answer to your question, but it would be interesting to know more about this, I think.
Okay, thank you, Alex.
Thank you very much, Alexander, for your question. Thank you very much, Alexander, for your presentation. And well, I think we have, unfortunately, no more time for questions or comments. I have also some questions, but I think we can talk later. And thank you very much again. So I think we will pass to the next speaker.
Thank you.
Thank you.
Okay, thank you, Alex. Chris, could you please share your screen, please?
Okay.
So the next speaker will be Christian Pick, and he belongs to the Mathematics and Physics Science Department from Exeter University. And you are not, okay, from Exeter University. And Christian Pick will talk about heteroclinic dynamics of synchrony patterns in phase oscillator networks with higher order interactions. Okay, go ahead, Chris, thank you.
Well, thank you very much, Alex and Thelma, for putting this session together. And of course, thanks to my previous speakers who introduced notions that I will come back to. I should say that the work I'm going to present very briefly today is joined with other people present in the session. So there's Alex Lose and there's Jose, who recently started working with me. And I'm going to briefly touch upon these things. But of course, there will be some side notes to even other people who are presently who are here. So let me jump in, and I want to kind of change the perspective slightly and add more to the confusion. Namely, I'm going to change tack from this saying that we have a network, a heteroclinic network from a graph, and what vector fields can we realize this, to going to a slightly more non-generic setting. Namely, I take a particular vector field and then I see what kind of happens. What are the heteroclinic phenomena in this vector field? And the vector fields I want to talk about are networks. So in that sense, we kind of have this usual overload of the dynamic of the word network, because on the one hand, the ODEs that I'm going to describe are network dynamical systems. So in some sense, and this is illustrated in this cartoon here, we have a whole bunch of nodes. These are the dynamical units by themselves, but they interact through each other like through network connections. So in some sense, just think about this as a physical network. You have a generator motor somewhere, you have a power line that connects them. So that's kind of the physical network. And then you have two ingredients, namely somehow the network structure, whom, and the network interactions, namely how does one oscillator influence the other oscillator, and they together give rise to the network dynamics. Sometimes these network dynamics can have networks in phase space, and that's kind of the heteroclinic networks that we're going to talk about. So there's two things to kind of keep in mind. So I hope that I can somehow distinguish the two, but I'll probably abuse notation and wording a little bit. So apologies for that in advance. So the main question, and this is the overarching question, is somehow if we know what node from the physical network, what node interacts with what other node and how they interact, what are the resulting network dynamics? So to make things a little bit more specific, what we're interested in a particular type of networks, fairly simple oscillatory networks, where we have coupled populations. So we have a number of populations that's indicated here by this index sigma. Each node in our network is given by an angle of theta. So it's basically just an angle on the circle. And you have that the network, or the population within, is all-to-all connected. You have that all the nodes are the same, and then you have a number of these populations and you connect them in such a way. The usual assumption that we'll make is that these oscillators are identical. So in the sense that they all have the same intrinsic frequency if uncoupled, and there's somehow a transitive symmetry operation. Namely, we can swap every oscillator with every other oscillator. And that gives, in the networks that we consider, rise to certain phase configurations that are invariant. So on the one hand, especially if you have these all-to-all connected networks of identical nodes, you have the configuration of full synchrony. So when all the oscillator phases take the same value, that is dynamically invariant. And you can have that like a splay phase configurations where the phases are distributed around the circle in a uniform way, is also dynamically invariant. So this is per population. So each population can either be in sync, or it can be somehow in the splay phase. And if you have multiple populations, then you can talk about synchrony patterns. Then particular parts of the network have different synchrony properties. So if you have one population, of course, this one population can be in sync, or it can be in the splay configuration. If you have two populations, you can have the sync-sync, or sync-splay, or splay-sync, splay, and so on. And you can generalize this in obvious ways to n populations. So for three particular configurations. So these are somehow synchrony patterns. These are dynamical phenomena that can arise in these particular network dynamical systems. So what do I mean by this? This is depicted here in this nice plot. So here I now take three populations of two oscillators. So simplest case, here's a little cartoon of what this looks like. So we have three populations, identical coupling within the populations, and then some global coupling that is a little bit different. This is what the dynamics look like. So here on the y-axis, we have the oscillators. Here on the x-axis, we have time. And here you can see that oscillators 1 and 2 in population 1, they have the same color. So effectively, the phase doesn't evolve. Oscillator 2, population 2, 1 and 2 have the same color, they're synchronized, but oscillator 1 and 2 of population 3, they do something else. And you might be able to see it, that the stripes here that indicate the phase is changing from black to white, and they're actually doing this slightly offset. So here you can actually see that this is in sync, but these are in this rotating wave configuration where you have the two oscillators on the opposite side of the circle, so they go around. And that basically, the coloring, I should have said this before, indicates what the phase is on a rotating color scale from white to black. So these are two of these synchrony patterns. Here, population 3 is in the splay configuration. Here, population 1 is in the splay configuration. The main question is, well, can I observe transitions between these synchrony patterns? So synchrony patterns have been studied in network dynamical systems as attractors, because you might want to use them to somehow encode information. And like a very far away universe, you might say that this resembles the brain, and a certain part of the brain is active if you want to store a bit of information. And this is one bit of information, and this is another bit of information that you want to store. But if you want to do information processing, then maybe you want to transition from one bit of information to the next. So can you see these kind of transitions between synchrony patterns? And of course, why am I showing this? The answer is positive. Yes, you can find these transitions, and that is given by heteroclinic cycles and networks of such synchrony patterns. So we have this structural network underneath, but in phase space, we have a network between basically these invariant solutions that are connected by stable and unstable manifolds. And I want to give you, in the last few minutes, or in the second half of the talk, an idea how these arise. To make things a little bit more concrete, what's the type of networks that we consider? So these are the typical equations that we have. So each oscillator has an intrinsic frequency, and then you have interactions that are through pairs of phases, through triplets of phases, and triplets of phases, and quadruplets of phases. And if you're interested in where such equations come from, Pete and Ana Rodriguez wrote a very nice paper where they explicitly calculated such equations from a phase reduction. So you take a general nonlinear oscillator system and you reduce it to phase equations, and you get these kind of interaction terms. what I'm going to do is, if I generalize this a little bit and I put some coefficients in front of here, because I don't necessarily want all of these things to be in here. And just to boil it down to the simplest case, I take 3 populations of 2 oscillators. That's effectively the network that you've seen before, where you only have this interaction here and where you have this interaction. So you look at the interactions between oscillators within the same population that is mediated by this pairwise interaction between phase differences. And then you have a whole bunch of these terms between quadruplets. But the weird thing is that the quadruplets only take 2 phase differences, namely from 2 different populations. And that gives additional symmetries, because now you get a phase shift invariance within each population, because in the end, one population only sees the phase difference of the other population and not the actual phase. So you have additional symmetries. And that makes the system fairly easy to analyze. So how do we get from there to heteroclinic dynamics? So this is the theorem that says basically that for 3 populations with 2 or 3 oscillators, you have a heteroclinic network that basically looks like this. So you have basically a cycle that goes from splay in the first configuration, sync in second and third, to basically the second population will desynchronize and go to splay configuration, and then the first one will resynchronize, namely it will go from splay into sync. And that is now a symmetric image of this. And in the end, we basically have a heteroclinic cycle that lies in the phase space of this network. So this is the heteroclinic cycle that exists. How to prove this? You first have to make sure that these 2 phase configurations, of course, are invariant. You have to make sure that they're linearly stable in the right way, that they have corresponding attracting and repelling directions. And the most complicated issue is to actually show that there's heteroclinic connection. If your network, if you only have 2 oscillators per population, then this is fairly simple, because the unstable manifold of 1 lies, the unstable manifold of 1 equilibrium that potentially connects to the stable manifold of the next equilibrium, lie in one-dimensional invariant subspace. So in order to show that there's a connection, just have to make sure that there's no equilibrium in between there. So that's fairly simple. If you now go to 3 oscillators per population, then you make the entire thing more complicated, because the connecting invariant subspace looks like this, like a triangle. And that means then that kind of connects to the discussion that Alex and Sophia started before. Not only have one connection, but an entire continuum of connections from this is the synchronized solution. This is the splay space solution. There's an entire continuum of connections between these 2 solutions. And in some sense, this network is not clean, because you necessarily have spurious equilibria that lie on these invariant lines here. I didn't have time to explain this in detail, but effectively somehow your network is embedded in a larger network where you have one-dimensional connections between these 2 equilibria. So in some sense, we have a kind of a non-complete but almost complete case. In any case, I think how many more minutes do I have? Just to kind of
3 minutes.
3 minutes. Okay, well, I'll just carry on then. So basically, this is what it looks like. Very briefly, this is the same kind of dynamics you saw before. So you have somehow, whenever you see these lines, you have a splay configuration, and you see cycling here between splay, sync, splay, sync, and so on. And you can see how this, basically how the trajectory cycles through the network. So this is for 2 oscillators per population, and here is the same for 3 oscillators per population. This is with a bit of noise, so that you don't have the exponential slowing down that you would have as you're attracted to the network. So to mention the work with Alex, we looked at not only the stability, explicit stability calculation for the case of 3 populations, but we also looked at networks of 4 populations with 2 oscillators. And then you can embed a network, a larger network into the phase space, namely where you have 2 heteroclinic cycles that share 2 joined connections. So after you desynchronize the 2nd population, you can either go to the 3rd population or you can go to the 4th population. So in some sense, you have you have a decision processor. You can switch along either one of these cycles. So you can prove that these networks exist, and you can then calculate the stability properties of the cycles within the network. So let me show you what this looks like. Again, this is a numerical simulation with noise. So here you have 4 populations of 2 oscillators, and here you can see that this one is in display, then the second one is in display, and then the third one is in display. Then you have first, second, third, first, second, third, first, second, fourth. So you actually see a transition around the other cycle of the network, first, second, third, fourth, and fourth again. So you actually see cycling. But again, these are simulations with noise, so you might expect some kind of switching between the 2 cycles anyways. And you can calculate the stability properties of this, which is a nice application of a class of heteroclinic cycles called quasi-simple, and using transition matrices, you can calculate this. Just to kind of use the last few seconds that I have to kind of outline a little bit of the ongoing work. On the one hand, there's this question about switching, and on the last slide, I showed some kind of transitions that are possible either to the 3rd or the 4th population. So Alex and I have been thinking about, okay, what kind of switching dynamics are actually possible in this network? Can you find trajectories that go to one side or the other side, or can we prescribe an itinerary? And the answer is, in the network that I showed you, not really, because this is fairly, I don't find the right word, rigorous structure. The problem is that these 2 cycles are related by a reflectional symmetry, and that means that there's a one-dimensional or codimension 1 invariant subspace that basically separates the cycle. So either you're on the one side or you're on the other side, but without noise, you actually don't find any switching dynamics. So the question is, can we somehow change the system in some way that we actually see some switching dynamics? So that's the first question. The second question is about symmetry breaking, because I picked out certain coupling terms. So the question that I'm looking at with Jose is, what's actually happening when you break the coupling, when you break this coupling degeneracy, because then the calculations become a little bit more complicated, because instead of relative equilibria, you have to look at tori. You have to look at the invariant manifolds of normally hyperbolic tori and how they intersect. So this is ongoing work, and with that, basically, I'm finished. There's a bit of higher order interactions that give rise to these phase dynamics. So it's really these triplet and quadruplet interactions that change the dynamics. Find all sorts of synchrony patterns and transitions between, and there are some questions, namely, can we observe something like that in an experiment? So there's a couple of references that outline the results, and I have to thank my funders. So I think I'm over time. So thank you very much for sticking.
Okay. Okay, thank you, Chris. Thank you for your nice talk. So questions, remarks from the audience, please go ahead. I have, in fact, 2 comments and a question. I guess that in your last slide, perhaps the 2 joint works are connected, to have switching and to have symmetry breaking, because in your case, you are saying that numerically you have not found switching And I guess that perhaps you need to make some symmetry breaking to have switching. This is something, this is just a comment. And with respect to the time series that you showed 2 slides ago with your joint work with Alexander, is there some regularity?
Regularity in terms
of the cycles that you in the previous slide in your time series. Okay, is there some regularity in which you can find some cycles, some preferred cycles to follow in the network?
So this is with homogeneous noise. So basically that kicks you with the same statistics into either cycle. So there's no regularity in the sense that they're both equal. You see equal statistics. Just regarding the question about symmetry breaking, yes, that is indeed true. That of course you want to break the symmetry to potentially get switching dynamics. We played around with this a little bit, and it looks like even if you look at return maps and you see what is mapped. What part of phase space is mapped into return map of the one cycle or the other cycle. Even if you break this reflectional symmetry that I was talking about, they're well separated. So without noise, at least right now, we haven't seen any way, even if you break this reflectional symmetry, to actually shove some initial conditions that go around one cycle into the bit of phase space that goes around the other cycle, because they're so well separated. Because even if you break the reflectional symmetry, you don't see this. So that just to kind of go towards the symmetry breaking.
But even with the noise, you cannot find switching.
No, with the noise with the noise you find switching. I mean that's what's shown here. So because the noise pushes you strong enough to push you into what goes along either cycle. But without the noise, you don't.
Okay. Okay. Thank you for the answers. So last questions to Chris. Okay. Once again, thank you, Chris, for your talk and for this discussion. So please stop sharing. And Peter, could you please share? Okay.
Yeah, one moment.
Okay. And now I give the word to Telmo. Telmo, are you here?
Yes. Can you hear me? Yeah.
Okay.
Well, it's a great pleasure to introduce Peter Ashun from the University of Exeter. He will talk us about computational properties of network attractors. So nice talk and enjoy, please.
Thank you very much, Alexandra and Telmo, for the opportunity to talk to you, and it's nice to meet up with some friends as well, even though we can't really meet up. And yeah, it's a shame that we can't sample the port as well. But anyway, I'm going to be talking about something which is maybe more going towards applications of heteroclinic networks and more general network attractors. So I will talk a little bit about heteroclinic and excitable networks and noisy networks, and then some applications of these to understanding computational systems. So I think Chris said somewhere off on a distant planet. Well, actually, it's the next talk. Maybe I'm off on a different planet, but never mind. And I'll talk a little bit about using network attractors, not just for sort of modeling natural computation, but also in neural networks. So I think Chris also sort of talked a little bit about different types of networks and networks. So just to sort of distinguish, you have sort of physical networks. You can think of functional networks that have express their dynamics in terms of changing of the functional state, and we end up with sort of logical networks, which is what I'm really going to be talking about. Is sort of relating the bottom two in this hierarchy of networks, and in the middle I'm talking, this is sort of putting the analogy for what's going on in natural computation in the brain and the nervous system. You have coupled neurons, functional networks. A lot of people are extracting these from things like EEG and trying to understand which areas are firing together. But actually, of course, it's the spatiotemporal patterns, not just the spatial, that are important for what we would call cognition, in terms of making decisions based on input and things like that. In artificial neural networks, you can think of the sort of functional networks as maybe the instantaneous state, and then the dynamical networks are phase-space behavior. And there, of course, you want to do some computation, and in particular, I'm interested in finite state machine type computations, how you can enact finite state machines using continuous time, continuous state systems. So the sort of problem that I'm trying to address in applications is how can you come up with a useful dynamical model for neural processes that could be the generation of spatio-temporal rhythms that encode some sort of pattern, the generation not just of knowledgeable sort of well-known sequences, repeatable sequences, but the generation of random sequences. And actually, that's a really important thing that we need to be able to do to generate things that have a particular distribution maybe, but are not deterministic. Working memory, how do you express that in a dynamical model? Perceptual rivalry is a particular example that's been studied an awful lot in neuroscience as a sort of a very simple example where the brain will generate some sort of switching regardless of input. So there's no input, but still there's some sort of cognitive dissonance on the input, some sort of rivalry in two things you're trying to classify, and typically what people do is they swap between them. And then more sort of generally finite state computations, how would you model them? Well, of course, you can model using attractors of autonomous systems, but actually that's going to ignore the input. So how do you bring the input back into the model? And of course, that means you're stepping into the world of non-autonomous dynamical systems. But let's typically, the way that you might do this is to try and identify the dynamics of an autonomous system that will have the responses that you expect to inputs. So a particular class of models that got me interested in all of this in the first place is the Lotka-Volterra type firing rate models of winnerless competition, where you have a number of firing rates of a number of neurons, and you have a self-excitation and a sort of a saturation term, and then you have some coupling. And for open sets of parameters in such a system, you can get robust heteroclinic networks with quite complex structure. However, this system has its problems in that the reason that you get robust heteroclinic networks is because you have some symmetries there. You have, well, not some symmetries, you have zero spaces, you have zero firing. If a neuron is firing at rate 0, then it will always remain firing at rate 0. And there are some problems with actually whether that's a realistic model. A few years ago, I was discussing this, especially with Claire Postlethwaite, and we started to try and generalize heteroclinic networks to dynamical networks that are sort of close cousins of heteroclinic, but ones that can appear maybe in more general systems, in systems where you don't require symmetries to be exact in order for them to be there. So I'll say some sort of invariant set in phase space is a heteroclinic network if it's there is a set of equilibria such that you are only the equilibria and you are connections between those equilibria. And we've heard Sophia, Alex, and Chris talk about such networks. Well, what happens if you consider networks where you don't start at the equilibrium, but you start close to the equilibrium? So you consider some amplitude delta, and then we'll start at some point that's within a delta neighborhood of one of the points and see which of those trajectories starting within delta of xi end up xij. So this is what we call an excitable network for amplitude delta. And in some sense, you can see a heteroclinic network is a sort of an excitable network for amplitude 0. There's not a lower threshold to get a trajectory that will transition from xi to xij. So in phase space, just to sort of distinguish, suppose you have xi 0, 1, 2, and 3. On the right, we have heteroclinic connections. So these are trajectories with alpha limit one of the xi's and omega limit another one. Here's an excitable network for delta, anything that's bigger than the black circle. So for example, if I take the red circle and I consider perturbations in there, there are some points there which are over the separatrix between xi1 and xi3, and there are other ones which are between xi1 and xi2. So you can think of this as then a sort of an index set of, for a set of equilibria in an autonomous system, indexed by delta, you get a set of graphs, directed graphs, that are all of the connections from one equilibrium to another for that delta or bigger. So of course, any multi-stable system, if you take a large enough delta, is an all-to-all graph. So the interesting cases are when you have small delta excitable networks, and those are plausibly the sort of structures in natural and artificial neural networks that can do computation given low amplitude inputs. So we are very well trained to sort of pick up quite small stimuli in the environment and use these to classify our actions. So I think Alex talked about this. You can get any finite transitive network, and subject to some minor restrictions, you can realize that as a robust heteroclinic attractor. So with a little bit more work, we came up with a way, this is with Claire Postlewaite again, a way of embedding one cycle free graphs, arbitrary ones, in a smooth system of coupled cells of dimension, the number of vertices plus the number of edges, that realize this graph as a heteroclinic or as an excitable network for arbitrarily small delta. So I'll give an example in a moment just to try and give a bit more intuition. So this is the graph. Okay, so we have a number of vertices. We have 3 vertices and 3 edges. This is the simplest one we could consider. So our embedding of this in a system with heteroclinic or excitable networks requires us to take 6 cells. So there are 3 associated with the vertices and 3 associated with the edges. We then couple them together in this way. So in fact, the P's, the ones associated with the locations that we want to stabilize as the sort of the states of the system are sort of mutually inhibitory coupled, but there are some sort of selective excitations. So the dashed and the solid lines sort of are associated with whether there's excitation or inhibition in some sense. So by choosing a set of parameters, I'll talk about in a moment, we can get this structure in phase space. So it feels like we've gone through an awful lot of work, but of course we started off with, this was a sort of a conceptual graph, a logical graph, and we've ended up doing what we wanted. We've got a heteroclinic network with the same graph there. But the advantage is we can also change one of the parameters, and these saddles undergo subcritical pitchfork bifurcations, so we stabilize these vertices. So we'll end up with the same structure, but this is now an excitable network for a finite delta. If you reduce the delta, then they all disconnect, and you just have 3 stable equilibria. And you can see that means that there are a number of sort of separating states that we have put onto the connections. And this is just the system. I should say G is a 5th order polynomial. The rest are constants, and there's some noise terms here. So for the heteroclinic case, the heteroclinic set of parameters, if I start off with a typical initial condition and draw out the blue, the red, and the black as the 3 components corresponding to the states, you see a cycling through the 3 of them with a characteristic slowing down, as you expect for a stable heteroclinic cycle. If you move the parameters to a location where you have an excitable network, it's rather boring without any input. You just settle down to the closest. You're in the basin typically of a sink. You just go straight there. If you add noise, you could then see, well, actually both of them are starting to cycle around. And this is something that we spend a bit of time looking at, is the sort of statistics of how the cycling, and whether in fact you can distinguish between these 2 cases in the presence of noise. So this brings me on to noisy network attractors. Can I just maybe check in, when am I meant to finish? Is it 40?
Yes.
Yeah, good, okay. So suppose now you have an autonomous system, which we'll write as x dot is f, x dot j is fj, and you now consider this as a stochastic differential equation where we have some additive noise independent on each component, with possibly a variable amplitude for each component. So we call these the eta j's. And we're going to assume that the x dot equals f of x has either a heteroclinic or excitable network attractor. Well, it's interesting to try and understand how this noise, which is a sort of a proxy for an input in a computational system, gets changed from being a sort of a microscopic noise on the state to a macroscopic noise on the finite states of the network. So we can do this as a sort of post-processing idea. We'll define k of x is the node that we're at the moment for some threshold h, and we can look at the last visited node k tilde. So that's the last k that you were at that's not 0. We call it 0 if you're actually not at a node. And so that means if this k tilde is I, we'll say that x is close to the ith node. And so we'd like to try and understand the long-term behavior of this this sort of this random variable k tilde, and we'll split that up into epochs, where we're going to say that we'll have an itinerary of epochs such that k tilde is equal to ij for all times between sj and sj plus 1. So sj and sj plus 1. At sj, you get a switch from your node ij minus 1 to your node ij. Of course, you spent some time wandering around in space before you get into the ball and get that classification. And you can look at the duration of this jth epoch to be tau j. And of course, this depends on x naught. It also depends on the realization of noise. So you've got a distribution of possible residence times at the jth node. So this is the probability that your residence is some time tau, given you've got to node j, and we'll look at the mean residence time, which is the just the mean of that, and the probability of the transition. Here's a few questions which we have only rather partial answers. Firstly, yes, what does the distribution look like? And what are the mean residence times at node j as a function of the parameters? What are the transition probabilities from j1 to j2 for any pair that are connected in the well, in fact, even if they're not connected, of course, you can get a transition when you add noise, if you add this Wiener noise. Under what conditions is the itinerary well modeled as a one-step Markov process? So, of course, when you're going to a heteroclinic, if you're on a heteroclinic network, you have this well-known phenomena of liftoff, that you can maintain knowledge of your previous trajectory even as you go past some of the saddles, and so that would be a barrier to saying in that case you don't have a one-step Markov process to determine these transition probabilities. However, conjecture that in fact in many cases that will be the case, and in particular for excitable networks. And this is an example of actually trying to compute that for a specific model from data, sort of reverse engineering it. So maybe I'll go on to this. So suppose you have the system as before. So this is with the 3-cell unidirectional ring, and we'll add noise to it that is with amplitude clockwise, this is eta clockwise, and in the bidirectional ring we've got two independent noises we're going to add. There's going to be a clockwise noise and an anti-clockwise noise. So again, here's some simulations to show you the sort of thing you would get. So cases A and B are for a heteroclinic, and C and D for excitable network attractors. So the left column is for unidirectional ring, the right column is for the bidirectional ring. And so you can see some of the features here, that in particular the noise for the heteroclinic networks tends to produce quite strongly periodic behavior, whereas for the excitable, you'll tend to get much more sort of variable residence times in the different states. And you can see, so this is, the right one is for equal noise, where you can see actually now we're starting to ratchet forwards and backwards around the ring in some sort of random manner. And for the bidirectional noise, for noise on the bidirectional ring, if we look at the two amplitudes, the clockwise and the anti-clockwise noise, you can plot out, this is sort of measured from a number of simulations, things such as the average residence time at any of the nodes. So that's the solid line. You can see as we reduce the amplitude, the noise, speed goes up. And if you can see the dashed lines, they correspond to the probability of doing an anti-clockwise transition. So not too surprisingly, as you get to much higher values of the anti-clockwise noise relative to the clockwise noise, you will get transitions in the anti-clockwise direction pretty close to 1. But I guess the remarkable thing here is that actually this seems to be pretty much like a sort of slightly warped polar coordinates. There seems to be a smooth dependence on both of these that maps out everywhere from 0 or some finite residence times up to infinity here, and smoothly the transition probability, the relative in the clockwise and anti-clockwise directions, moves from 0 here up to more or less 1 there. So this was the case for heteroclinic connections. The same sort of thing appears for excitable connections, but with a new feature, and that is there is, of course, for excitable connections, there's a threshold associated with this delta. And so you actually get a very steep rise in the transition probabilities as you get close to that delta. And what's more, you start to see less and less importance of the clockwise and anti-clockwise motions relative to which direction it actually goes. Okay, so on to an application, a network attractor of a realization for a Turing machine. So a Turing machine is a finite state computing machine which has a number of internal states, including possibly a number of halting states, and it has an interface to an exterior storage, which is seen as an infinite paper tape, each site of which has a finite number of symbols. So you have an internal state and you have a symbol. You read that at the current state, and then the machine does one step to the right or left on the paper tape. It writes on the paper tape and then does a transition. And these systems can have remarkably complex behavior, even for small numbers of symbols and small numbers of internal states. So in particular, there's something called the n-state busy beaver. So a busy beaver is a machine that you give it a starting state, and among all machines of that complexity, it takes the longest to get to a halting state, but it gets to a halting state. So the 3-state busy beaver, you can see this has 3 states. You start in state A, it sort of jumps around between states A, B, and C, eventually ends up in state H. And you can see what it's doing. This is the paper tape. It starts off with all zeros. It writes a 1. It shuffles it backwards and forwards, and somehow it takes quite a few states to get to the halting state. Now, of course, there are different ones depending on whether you have the maximum number of instructions before you halt, or the maximum number of symbols written before you halt. But the so depending on the number of internal states, and this is just for 2 symbols, you can see that these number of maximal states before you terminate and the number of the number of tape marks and the number of steps grows like a rather crazy function of n. So in these cases, these are results that are sort of rigorous, that show there is a busy beaver on 6 states that will definitely halt, but you don't know whether it's going to take more than this rather large number of steps before it gets there. So we were rather impatient, so we stuck with the 3-state busy beaver and came up with a way of sort of putting all of the actions into this. Maybe I should go over this into an excitable network attractor that we could then explore its response to inputs, which would be from the tape and also noise. So if we start off with, this is the 3-state busy beaver transition diagram. So you have these 3 states, you have the halting state. At each point when you do a transition, you always write a 1, but whether you read a 1 or read a 0 depends on whether you go this direction or the other way, and the right and the left correspond to whether you move the paper tape to the right or the left. So the first thing to note there is, of course, we can't embed this as a heteroclinic or excitable network because it's got this 1 loop. So the first thing we need to do is to break up that 1 loop, but the method we were using doesn't worry about 2 loops, so these ones are fine. And in fact, there's also a delta clique in there, but again, our method didn't worry about that. So the sort of picture we have is, this is our dynamical system, which consists of a number of cells. So there are actually only 4 of these cells. So there are 3 cells plus the halting state, and then you have these corresponding to the connections. We have noise input here, and then we have an input that is just a constant vector applied to the state in the system. So that seems a fairly reasonable thing to do. The most complex thing we need to do is to identify which of these is a maximum and say, okay, that says which state we're in, and will result in a left or right motion of the paper tape. So running this with low noise, you get this sort of behavior, and it stops quite nicely after writing 1, 2, 3, 4, 5 states. And these are just to try and convince you that we really did run some ODEs here. So we got the P states, which do the classification, and then the Y states, which turn on when you have a transition from one to the other. But if you start to add noise to this system, which is what a real computational system will do in a natural computing system, of course, you won't reliably always make those transitions. And in the last part, I would like to talk a little bit about quantifying computational errors using this particular machine, which is a sort of useless machine. It's not quite a Turing machine because it never stops. But you have 4 states, and you have 8 possible transitions. And then our tapes are all 0, and we write nothing, so it's really useful. And then we just look at the transitions of this system, in particular looking at the noise. So if this was an accurate realization of this machine, what you would end up doing is always going sort of anti-clockwise around this diagram. So this corresponds to there being a correct transition or no error. If we have a clockwise transition, then this corresponds to, in some sense, a read error. So it's as if you'd read a symbol 1 at one of the sites. However, there are also transitions you can get that are not associated with either of the correct readings, and we call those wild errors. So using either excitable or heteroclinic networks, I can't really explain what the eta is at the moment, but this is just a parameter in the model. You can see then that you have, so the blue is showing read error rates and wild error rates in red. So you can see, yeah, so hang on, which one is A and C? This is the excitable network. So the residence time is increasing as we increase the noise, whereas so we got noise on some of the other components, I should say, and you can see that as eta, as the noise increases, you actually paradoxically increase the residence time here, but the error rate is going up. So this is just a sort of a cartoon showing this diagram and the response. So this is now, we have a noise and we have a signal for this realization of a Turing machine. And you can see in the excitable case, you have a threshold associated with the amplitude where you get the connections that you want. And if you can exceed that with your signal, then you'll get correct transitions with few errors. If it's the noise, which is the thing which is driving it, then of course it will do transitions, but with more errors. I still got a moment, so maybe I will also just briefly mention some other work that I've been doing. This is with Andrea Ceni and Lorenzo Levi. So Andrea was a PhD student who has just finished his PhD, and Lorenzo was a computer scientist interested in echo state networks. So there the problem is you have a trained recurrent neural network, which is partly a random network. So you have a nonlinear set of nodes here that are recurrently and randomly connected. And the strange thing about echo state networks is that they work even though you maintain a random network here. What you do is you train the output. So you've got some feedback here. So as you do that training, you are modifying the nonlinear dynamics of this network. And we were working on the hypothesis that, in fact, in certain situations, this trained echo state network is actually using network attractors to do its computations. Although I should say this is a high dimensional system, so the first problem is to try and detect attractors and then to try and find excitable connections between them. And the particular system that we looked at, this was inspired by work of Susilo and Barak from a few years ago. It was a flip-flop task where you say, okay, I'm going to try and train my echo state network using a sample where the task is to flip the output if you get a positive pulse, but you make it positive, and you flip it negative if you have a negative pulse. But you're going to try and do that simultaneously for 3 inputs. So you've got 3 inputs and 3 outputs. This clearly needs some internal memory. So you need multi-stability, and this was sort of the outcome. After doing a round of training of this network, we then sort of, that's a training phase, you then put it into practice and say, okay, how well is it trained? And one of the, so I think most exciting things of this was something we didn't expect. You can start to see mechanistic interpretation of errors in this system. So in particular, this is the black shows what the target output should be for some sequence of inputs. And you can see the red is the actual generated output after a training period. And you can see it's done a pretty good job, but actually occasionally it does this funny sort of little lump here before this transition. And it turned out that you can explain these as being extra states that have appeared in the trained graph. So the bottom here shows a realization of the sort of a representation of a noisy network attractor, an excitable network attractor for this trained system, where the numbers represent some sense the sort of the strengths of transitions between these 6 states. So this is for just a 2-state input, 2-state flip-flop. You would expect to get only 4 classifying states. In fact, you'd ended up with 2 extra ones. Okay, so just to wind up, I hope I've convinced you that nonlinear stochastic dynamics with network attractors is a useful model for natural and artificial computational systems. It is a sort of, I could think it gives you a vocabulary to start to talk about things like signal to noise trade-off and robustness of computations in these continuous time, continuous state systems. I talked about relevance to cognition and machine learning tasks, in particular the machine learning ones with Jenny. I've also looked at applications to modeling rapid transitions between EEG microstates. This is with Kreisa et al. We've also been taking this further to try and find arbitrary excitable networks in the sort of recurrent neural networks that actual people working on recurrent neural networks like to use, rather than the ones which we've dreamed up. So thanks for listening, and here are some references. So in particular, this one is the one I just mentioned, is excitable networks for continuous time recurrent neural networks. That's on archive at the moment. Thank you very much.
Thank you very much for your very, very nice talk, Peter. So, well, we have Alexander come back again. He has some technical problems. Sorry for this. Any comments, questions? So the participants can write on our questions and answers box. And well, I have a naive question just for the introduction, sorry. Why the word excitable? Because it means it have a meaning for sure.
Yes, it has a meaning. That's a good point, actually. I should have said something about that. So excitable dynamics is usually used in neuroscience to indicate that you have a stable equilibrium and you have small perturbations will still give a large response. So that's really exactly what we've got here. We've got a stable equilibrium here, but small perturbations in certain directions will give a large response. Maybe if you have a number of excitable units and you couple them together, you may end up with an excitable network in the sense that I'm describing, but you may not. It's also possible that you have units that don't have excitability, but when you couple them in a certain way, you do find excitability in the network. And so that's what I'm trying to sort of highlight here. it's a useful concept to work in the sort of combined phase space. Yeah.
Okay. In this particular case, we are adding equilibria to the system. Okay. There's a particular kind of perturbation.
Well, yes. So you can see from going from this one to this one, yes. If you have a parameter that changes, that where Psi1 does a subcritical pitchfork bifurcation.
Yeah.
That's the particular model, I guess.
Okay. Any other comments, questions? You are off, sound off. Yeah.
I have some questions. Peter, thank you for your talk. So I missed some parts of your talk due to technical problems. The first question is, suppose that you have excitable network. Is it chain stable in general, or because the definition of excitable is very close to the definition of chain stability?
I guess it's so you mean sort of Conley type,
like pseudo shadowing.
Yes, it's a sort of pseudo shadowing, but not for arbitrarily small perturbations.
Okay.
It's so you need really so like a proper excitable network. You have to have a finite size perturbation to get you from Psi1 to Psi3, say.
Okay. The other question is, you have some results when the noise is sufficiently small. How small is the noise? It should be very, very small. How small? In your numerics?
Yes, we have a lot of numerics. We have a SciAds paper from 2016, I think, where we look at some of the asymptotics in the case where you have sort of two outgoing connections. Basically, if those are rigorous, I guess it's asymptotically small noise. Then you get sort of a Kramer's type of transition rate.
Okay.
Yeah, and I should just maybe I did have a picture there. I could have. So this is numerics, and this is using a sort of Kramer's type approximation.
Okay. Okay. And my last question, the last question is, you have a slide. So once again, I missed some parts of your talk. We have a slide in which you distinguish between two cases: nu greater than 0 and nu less than 0. And for nu less than 0, you have heteroclinic cycles.
Yeah.
And for what is the role played by nu in this case?
Yeah. So I guess let me get the right one. Where's it gone? So this result is a construction that gives you a set of differential equations with a parameter nu, such that if nu is, I can't remember which sign, is one sign, you have heteroclinic realization. If it's the other sign, then you have an excitable realization with amplitude that is basically square root of nu. So because you have this subcritical pitchfork bifurcation that stabilizes the nodes in the heteroclinic network. Yeah.
Okay.
There is a question from Pedro Duarte. Well, I can read. Can you estimate the probability of getting the correct answer when simulating a Turing machine?
We can get bounds on the noise, I guess, when that's small. But let me just get to. Yes, so we can get sort of heuristic expressions here, but only in the sort of the limits of low noise can we really get asymptotic expressions.
Okay.
I don't know if I don't have a more precise picture than that yet, but you can get it as you'd expect to do correct transitions an arbitrarily large proportion of the time by choosing your noise small enough.
Okay. Well, I think we are in time. Thank you very much, of course, Peter, for your talk. Thank you very much for all the participants who had assisted to this session. And well, thank again to all of the speakers, Sophia, Alexander, Christian, he had to come out, and Peter, thank you very much for had accepted our invitation and do this. I think it was a great session. And well, these are, of course, my words, and from Alexandre Rodrigues also. It was a pleasure to organize this session. Yes. Thank you very much. We hope to see you soon, and enjoy the rest of the national meeting. I think it will be a great meet.
Okay, thank you once again to the speakers, and to Telmo as well, and to the audience. No. Bye-bye.
Bye.
Thank you.
Thank you very much.